Last class I told you that I'm going to collect the book to show you the derivation of the non-inverting amplifiers derivation, but I could not collect the book yet, so I'm not doing that in today's class. However, we are going to continue the lecture, and we're going to see for the further parts that we have. This is the circuit symbol for an LED, and using a comparator circuit, that we have seen in earlier, for example, this kind of circuit in the output side, we can have this kind of opposite two LEDs. You can have this kind of two LEDs. These LEDs are useful to give us two different type of signal based upon the two different type of output, op-amp output that we have. For example, if you have a look over here, this is ground connection, which is 0 voltage. So it is the op-amp output. If the op-amp output is highest positive, that is, then D2 will be blocked, but D1 will be allowing the current, and as a result, we're going to have some illumination in the diode 1. But reversely, whenever the op-amp output reverses, let's say if the op-amp starts to give negative voltage, then the current will start to flow from ground through the D2 and eventually go to the op-amp. As a result, D2 will glow and D1 will switch off. So based upon the type of op-amp output, if we have these two diodes which are placed in opposite polarity, then we can have individually different outputs. This is just one way to show that the op-amp output can be used or can be utilized to have two different visual outputs. In these places, we can also have some sort of silent mechanisms. If we want some audio output, in this case, we can have some other kind of electromagnetic devices. For example, some electromagnetic clutches can be used, which is very commonly used for the case of air conditioning units. That's how they operate for a fixed temperature. In which case, the sensing device is a thermistor, not an LDR. So that is also pretty important. So this is actually one of the key part. And where is the back EMF thing? Did they delete the back EMF thing? Oh no. Here we have a thing that is called back EMF. A part that using the so this was for the LED. I actually talked about the LED first. I forgot to discuss about this. Coming back to over here. Within this part, this is actually this whole thing is the circuit symbol for electromagnetic relay switch. So in this case, this rectangular box represents a solenoid, and this circuit will be activated by some current from some source, which in turn, if magnetized, will attract this switch, and this switch will be closed because of the attraction. This is always made with a soft iron switch. And whenever this solenoid will be energized, whenever we say energized, basically it means that the solenoid is now having a current flow through itself. So if the solenoid is energized, then magnetic attraction will close the switch. When the solenoid will be de-energized, or it will the current flow stops, then this switch will be automatically open. So this is actually the relay symbol. How can we use this kind of symbol for our purpose? For example, we have a simple circuit over here. Take a very good look at this circuit. I'm going to take a screen. I'm going to take this out so that I can draw it in the MS Paint and discuss something about it. Okay. So the way this thing is going to work is that let's say this circuit is designed for such that this solenoid should be energized when the op-amp is positive output. So if for positive output, our switch will be closed, and the device over here, whatever the device that is placed over here, that will run. For negative output, that D1 will not allow the current flow, so this will be open, and the switch will be this device over here will not run. So positive output basically means this is the high potential, this is the ground, is zero potential, so current can flow through it. As a result, the solenoid will be charged, and this will happen. Now you might wonder, why do we have this thing? What is the purpose of this thing? This diode 2 over here is placed to stop the back EMF. Now there is a term called back EMF. Back EMF is not very elaborately discussed in your syllabus, but I'm going to give you some idea because I want you to understand what is the concept of the back EMF. Try to understand one thing. You guys remember Lenz's law, right? What is the basic idea of Lenz's law? Actually, Lenz's law can have a lot of different explanation. One of the simplest way that by which we can express Lenz's law is that any magnetic material doesn't want to have a change of its magnetic state. I shouldn't say magnetic material, I should say any conductor. Any conductor does not appreciate a change of its magnetic state. So if a conductor is unmagnetized or demagnetized at this state, it will preferably try to keep it, which means whenever you're trying to magnetize it, it will produce an opposition towards it. Since in the same way, vice versa, if you're trying to demagnetize a coil, it will naturally try to produce a way so that it can remain magnetized. So Lenz's law basically gives us the idea that any conductor has a tendency for a reluctance or an unwillingness to accept a change of its magnetic state. If it is magnetized, it will want to remain magnetized. Uh, if it is demagnetized, it will want to remain demagnetized. So whenever we are going to change the state from one stage to another, then it will show some reluctance, show some opposition, show some obstruction against that change. That's one of the ways by which you can talk about Lenz's law. So the reason I'm telling it in this term, because you can see over here we have a solenoid. This rectangular thing is a solenoid. So what will happen? Let's say at some point we have some positive output. So some current flow is flowing through the solenoid, and this switch is closed. As a result, whatever the device that we have over here is running fine. Let's say after some time, by means of the change of some physical variable, this op-amp output changes from positive to negative. So whenever the op-amp output will change from positive to negative, the current flow in this circuit will stop, which means the solenoid will try to become demagnetized because the current flow will not be provided. But by Lenz's law, the solenoid will want to maintain its magnetization. So the way it's going to work is that whenever the current flow from the op-amp output starts to get lowered, starts to become smaller, the solenoid itself will produce an EMF across itself. The solenoid will produce an EMF across itself so that the current flow shouldn't be stopped, which means it will try to draw in current so that it can maintain its magnetism, which basically means in this case the solenoid will produce a positive voltage of its over here and it will produce a negative voltage over here. This EMF that the solenoid produces is actually happens for a very short duration. It is only created, it is only produced in the solenoid coil, as long as the current is undergoing a change. So for the duration the current flow drops from maximum value to 0, this solenoid will produce a pretty high voltage. Now, interesting thing you need to understand, have a look at this diode. This diode is in forward bias, right? This diode is forward bias. Whenever the solenoid produces some voltage of its own, it has a tendency to produce a really high amount of current through the op-amp output. Now, this will lead to some pretty significant problem, because if I draw the op-amp over here, let's say here is the op-amp over here, and these are the two inputs that we have, and inverting input, non-inverting input, and here we have the two supplies, let's say negative supply and positive supply. So whenever, because of the back EMF, a very large current tends to flow through the op-amp components and eventually through the op-amp output. This large current can be detrimental, can significantly damage our op-amp device, which we don't want to have, which we don't want to happen. So এই পর্যন্ত বোঝা গেছে কিনা যে because of the reluctance of the solenoids to become demagnetized, it will produce its own EMF so that it can maintain its magnetism, and that voltage that the solenoid will produce will cause a really high current that can flow through the op-amp device, which is a semiconductor device, and that can potentially damage our op-amp op-amp semiconductor. এই ড্যামেজটা হইতে পারে। এই কনসেপ্টটা বুঝা গেছে কিনা? বলবান।
Yes.
ঠিক আছে? So now we want to make a bypass path so that whenever the solenoid will always produce this back EMF. There is no way for us to stop the solenoid to produce a back EMF. Back EMF is a default outcome of change of current. So what we want to do, we want to provide an alternative bypass path so that this solenoid's back EMF should not affect our op amp. So what can we do? That's where this additional D2 branch is coming by. So let me just place the figure one more time. Now you should be able to see it a bit more clearly. So now have a look over here. I'm drawing in the green. So whenever the op amp, whenever the solenoid produces its own high voltage, we produce an alternating path. So this could very well be only a single wire. This could be a very well be a single wire. So the purpose of this single wire would be that whenever this solenoid is trying to draw more current, this is positive or negative, no big deal. You can draw in the extra current through this path out of the this path, and this current will flow through this loop for a small duration, and the whole thing will be just fine. So the current will go through a very small circuit, but not affecting our op amp that is connected over here, so that we can save the op amp. So a single piece of wire for bypass should do the trick. But there is a catch. The catch is, if we do provide only a piece of wire, then there is a problem. The problem is that the expectation of this whole circuit, getting back to the first circuit, have a look. The expectation of the whole circuit was that when the op amp was giving us positive output, this solenoid should energize, which means current should flow through the solenoid path. But from this point, if we do have an alternative path, you do understand that when the op amp output would be positive, current can basically flow through this path back to the ground. This is, I'm talking about when the solenoid is supposed to be energized, current will not flow through the solenoid. Current will rather prefer to go through the zero resistance or the least resistance path, and the solenoid will practically not serve its purpose. So we don't want that to happen either. So when the op amp gives us positive, current should flow through the solenoid, and when the back EMF is produced, current should not flow through the op amp. That's our expectation. To prevent the current flow through this path downwards when the op amp output is positive, we provide this D2 diode. So what does the D2 diode do? This D2 diode basically makes sure that when the op amp output is positive, current actually flows through D1 and through the solenoid, and eventually goes to the ground. As a result, the solenoid is energized and the switch will be closed. It makes sure of this so that the current cannot pass through this left path. But whenever the back EMF is produced, it will allow the high current flow through this path very well, and eventually this will automatically be managed within the small circuit that we see over here, and the op amp device over here can be protected from potential damage. So this is why we need to have both of these diodes, D1 and D2, in place. D1 is required to determine what kind of output should energize our solenoid. So এখানে যেহেতু D1 এর direction downwards, which means current flow should be allowed by downwards, which basically means for this circuit, positive output from op amp will energize the solenoid, and D2 should be aimed in the upward direction, representing that D2 is stopping is here to provide the alternative path for the back EMF. However, the purpose of the diode is to stop the current to flow through itself when the output is already positive. এটা ভাইস ভার্সা হতে পারে। ভাইস ভার্সা হতে পারে কিরকম? যদি আমাদের আসসালামু আলাইকুম। Sorry about that. So the other thing that we can have is that how can we reverse the circuit? How can we reverse the circuit? So for example, if you want a similar mechanism to work for us, that when the op amp output should be negative, this solenoid should be energized. Simply, we need to reverse the orientation of these two diodes. So basically, what we can do is, if this is supposed to happen, then we should have this two flipped. So this one should look like this, and this one, that case, look like this. So if we have this orientation, in that case, this circuit will work when the op amp output is negative, And if there is a positive output, this solenoid will not be energized. And in the same way, the back EMF can be operated on its own within the small circuit that we have. So এই হচ্ছে ব্যাক ইএমএফ এর বেসিক আইডিয়া এবং D2 ডায়োডের পারপাস। এই জিনিসটা বোঝা গেছে কিনা বলা পান? এই পিচি সার্কিটটা পরীক্ষায় আঁকতে আসে। সো এটা প্রপার অরিয়েন্টেশন আঁকতে পারলে ভেরি গুড, আর প্রপার অরিয়েন্টেশন আঁকতে না পারলে মার্কস কাটা যাবে। এনি কোশ্চেন? অ্যাপারেন্টলি নো। আচ্ছা, এরপরে আমাদের এই পার্টটুকু শেষ। এখানে আমাদের একটা 3 নাম্বারে একটা ছোট হেডিং আছে। এই জিনিসটা ভালো করে আমরা পড়ি। এখানে কিছু ছোট কিছু ইনফরমেশন দেওয়া আছে যেগুলোর উপর বেস করে আমাদের কোশ্চেন হয় খুব কম, বাট এই জিনিসটা কনসেপ্টের জন্য ইম্পর্টেন্ট। আমি এই পি হেডিং পুরোটাই পড়তেছি। তোমরা এই বাকি যে জিনিসগুলো আজকে পড়াইলাম সেই জিনিসগুলোর ডেসক্রিপশন নিজেরা পড়বা। না বুঝলে আমাকে অবশ্যই জিজ্ঞেস করবা, বাট আই এম গোইং টু রিডিং থ্রু দিস থিং। Candidates should be able to show an understanding of the need for calibration where digital or analog meters are used as output devices. Candidates should be able to show an understanding of the need for calibration where digital or analog meters are used as output devices. So, এখানকার কি আইডিয়াটা হচ্ছে যে, first of all, let me explain what is calibration. Calibration basically is marking a certain sensing device so that it can give us some quantifiable data. কিরকম? Simple example বলি। Let's say a thermometer is made perfect. So it's the length of the mercury column rises uniformly with temperature rise and falls uniformly with temperature drop. If you are only given a thermometer of that shape where it does not have any degree Celsius or any grading marks, I mean all those temperature measurement marks, if you only have the glass thermometer and there is mercury within the glass thermometer and there is no mark around, this is a good thermometer, but this is missing the calibration. Using the thermometer, you cannot take a temperature reading. To be able to take the temperature reading, this should be marked with the temperature scale, and that's what makes it usable. So the process of doing that, the process of preparing a component so that quantifiable data can be obtained out of that device is what we call calibration. Calibrationের বেসিক আইডিয়াটা হচ্ছে যে আমরা একটা সার্টেন নতুন ডিভাইস যখন বাই করবো বা আমরা সার্টেন নতুন একটা ডিভাইস যখন আমরা 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 অ্যাটাচ করবো কোথাও, তখন স্ট্যান্ডার্ড আরেকটা ডিভাইসের সাথে কম্পেয়ার করে আমরা সেই জিনিসটাকে ক্রিয়েট করব। ফর এক্সাম্পল, আমি বোঝানোর জন্য বলি, ইফ উই ওয়ান্ট টু মেক thermometer, let's say mercury thermometer from scratch means not using another thermometer, just by using the property of water. In that case, it can prove to be pretty difficult because we have to be very careful that we are putting whenever we are defining the 0 degrees Celsius, the lower fixed point, we have to put the thermometer in crushed ice, and that it should be kept within in contact with crushed ice for a pretty long duration so that we make sure that the thermometer mercury level is at the very bottom level, and it should not be in contact with the water that it produces. So all the crushed ice should be placed in a funnel. So আমাদেরকে এই কন্ডিশনগুলো ফুলফিল করতে হবে, which is doable. Not so difficult. But if you're trying to determine the upper fixed point, which is the boiling temperature of pure water under 1 atmospheric pressure, this 1 atmospheric pressure is very important. If you want to achieve that, in that case, we have to keep it at steam of exactly 1 atmospheric pressure for a pretty long duration so that the mercury level is at a stable level for where it should represent 100 degrees Celsius. Doing this thing every once in a while can prove to be pretty difficult, but that's how calibration is done for a thermometer. What else option do we have? If we have a properly calibrated thermometer that we know that it's true and that is accurate, then we can use it to calibrate other devices. For example, you have a steel ruler, let's say. The steel ruler has some markings on it. This steel ruler was not made by the scientist in the scientist by the units and measures thing. This was made by a certain factory who have a reference scale which they obtained from the original length measurement authority, and they are copying that thing and printing that scale onto the steel ruler. So we are using that thing as a reference for further production. So this is how pretty much calibration is done. So whenever we will do some calibration, it is important that we know how the device behaves. We should know how the device behaves, and that behavior should be projected properly on the sensing device so that quantifiable data can be obtained. So let's have a look at this part. An LED may be used to indicate whether an output is positive or negative. If the output is from a comparator, then LEDs can give information as to, for example, whether a temperature is above or below a set value. However, the LED does not give value of the temperature reading. So this is pretty important. Using a comparator circuit, we can only determine whether the temperature of the room is more than something or less than something. That's all we can say. Because whenever it will be more than something, more than that you have predetermined value, it will give us one type of output, and whenever it flips, it will give us the other type of output. So it can only tell you whether it is above or below a certain predefined temperature, but it cannot specifically give you what is the exact temperature. So it cannot do the job of an exact thermometer, but it can do the job of whether the temperature is above or below that much information. Sometimes that much information is good enough for devices, for many appliances. For example, let's say if you operate an industrial freezer, it might be important that you have to keep the temperature lower than -8 degrees Celsius at all points. You should never get above -8 degrees Celsius. For industrial freezer, that's I think, yeah, as far as I know, it's -8 degrees Celsius. So this is a pretty important factor. So you can simply attach one of these comparator circuits where you can set the temperature sensing line value at -8 degrees Celsius, and you can have simply two lights showing you that green and red. Let's say showing green means the temperature is below -8 degrees Celsius, maybe -10, maybe -11, maybe -100. We don't care, but as long as the temperature is below -8, you have a green light. And then as long as the moment the temperature goes above -8 degrees Celsius, it will immediately switch to some other color, maybe red. So it will tell you some decision making information, whether this or that, but will not give an exact temperature. second paragraph second paragraph tells us what many sensors, for example a thermistor or an LDR, are non-linear. It was seen in 28G that the sensor could be connected into a potential divider circuit, so that the output of the potential divider varied in some property, for example temperature or light intensity. This variable voltage could be measured using an analog or digital voltmeter. So what kind of voltage are we handling? We can actually do that. It's pretty simple. I don't actually explain this. The reading on the voltmeter would vary with the property being monitored. However, the reading on the voltmeter would not vary linearly with change of the property. In order that the property can be measured, a calibration curve is required. Calibration curve কি জিনিস? Calibration curve হচ্ছে এরকম একটা গ্রাফ। গ্রাফ এরকম একটা গ্রাফকে আমরা বলি ক্যালিব্রেশন কার্ভ, যেখানে আমাদের রেজিস্ট্যান্স ভার্সেস টেম্পারেচার ভ্যালু দেওয়া আছে। সো আমরা ডিভাইস থেকে মেজার করব রেজিস্ট্যান্স, সেখান থেকে আমরা বের করে নিয়ে আসবো হচ্ছে temperature কত হয়. So if we have a graph like this, if we have access to a certain graph like this for a certain component, then measuring one physical quantity can very easily be calculated or projected to find out the other physical quantity. So that's what means by calibration curve. The next thing that we have is that the reading on the voltmeter is recorded for known values of property X. The reading on the voltmeter is recorded for known values of the property X. Now, they are saying property X because this X property for thermometer, sorry, the reading on a voltmeter is recorded for known values of property. This property X could be anything. For example, if you're using a resistance by strain gauge, this property X is resistance. If you're using an LDR, this property is light intensity. If you're using a thermistor, this property is temperature. If you're using something else, this property could be something else. But the voltmeter, the reading on the voltmeter that you get from these sensors is recorded for known values of the property X. A graph is then plotted showing the variation of the property X of the voltmeter reading. The value of the property X can then be read from the graph for any particular reading on the voltmeter. So what it means is that, let me just draw. If we are trying to calibrate a certain device, we need to have a measurement device. And let's say if we are trying to make a graph for, let's say, what? Let's say light intensity versus resistance. Resistance versus light intensity. তারপর এটার একটা গ্রাফ আমরা করতেছি। ঠিক আছে? সো প্রথমে আমরা যে কাজটা করব সেটা হচ্ছে আমরা একটা ওহম মিটার ইউজ করে স্পেসিফিক কিছু রেজিস্ট্যান্সের জন্য, স্পেসিফিক কিছু লাইট ইন্টেন্সিটির জন্য স্পেসিফিক রেজিস্ট্যান্স ভ্যালুগুলোকে আমরা প্লট করব। সো আমরা এই জিনিসটাকে প্লট করলাম। Once we have plotted this thing, we get the calibration curve of the device. So আমরা এরকম একটা calibration curve পেলাম। যত বেশি লাইট ইন্টেন্সিটি বাড়বে, আমাদের এলডিআর রেজিস্ট্যান্স তত কমে আসতে থাকবে, which totally makes sense. Now, once we have this curve, then we can use this curve to find out the resistance without having using the ohm meter. Then directly by plotting some value of the light intensity, we can directly calculate resistance, or vice versa. Directly by measuring the resistance, we can directly calculate the relevant light intensity that we are trying to measure. So, but it is important that we must have access to a calibration curve at the beginning. And how can we do that? By doing experiment with this device, recording some exact number out of this device, and then plotting that thing on a graph, and that gives us access to calibration curve. Without having a proper calibration, any device is useless. মনে করো তোমার একটা সার্টেন ডিভাইস আছে, যে ডিভাইস কাজ করে ঠিক, প্রপারলি কাজ করে, কিন্তু রিডিং সব ভুল আসে। এই ডিভাইস দিয়ে আসলে আমাদের কোনো বেনিফিট নাই, আছে? সো ক্যালিব্রেশন ভুল হলে আমাদের ওই ডিভাইস দিয়ে কাজ হবে না। যেমন ক্যালিব্রেশন ভুল হওয়ার একটা কমন এক্সাম্পল হচ্ছে, ক্যালিব্রেশন ভুল হয় না, এটা অ্যাকচুয়ালি পার্সোনাল এরর। ফর এক্সাম্পল, মাইক্রোমিটার স্ক্রু গজে যে জিরো এরর হয়, আমরা যদি জিরো এরর খেয়াল না করি, তাহলে আমাদের সবগুলো রিডিং কি হবে, একটু বেশি হবে অথবা একটা ফিক্সড অ্যামাউন্টটা কম হয়ে থাকবে। দিস ইজ শোন এজ এ সিস্টেমেটিক এরর, বাট this is a systematic error. Actually, it's not a personal error. This is a systematic error because this is a error developed from the device. But doing the experiment carefully, a person can logically avoid this error. And person should be an experimenter should be careful to avoid this error. But if they don't do this, then we'll have some amount of error within this device. So a device that has some error within itself cannot be said to be uncalibrated or miscalibrated. It is just some fixed amount of error. But if it so happens, if it just so happens a device is just miscalibrated, for example, মনে করো একটা certain সেন্টিমিটার স্কেলের স্পেসিংটা অনেক বড় হয়ে গেছে, ওয়ান্ডার স্পেসিংটা কেমনে বড় হবে, মনে করো সামহাউ ম্যানুফ্যাকচারিং এর সময় এটা একটা ফল্টি ডিভাইস ছিল, সো দ্যাটস ওয়াই আমাদের মিলিমিটার গুলা যতটুকু গ্যাপে হওয়ার কথা, মনে করো মিলিমিটার 1 মিলিমিটার গ্যাপ এক্স্যাক্টলি 1 মিলিমিটার হয়, মনে করো 1 মিলিমিটার গ্যাপ এক্স্যাক্টলি হয়ে গেছে হচ্ছে 1.002 মিলিমিটার, মনে করো এই পরিমাণ গ্যাপে আমাদের মিলিমিটার মানগুলো পড়ছে। তাহলে কি হবে, whenever we're going to measure some pretty long distances, at one point we're going to have some pretty significant error. So এই টাইপের প্রবলেম হইতে পারে, বাট এগুলাকে আমাদের প্রপারলি হ্যান্ডেল করা লাগবে। এটা হচ্ছে ক্যালিব্রেশনের বেসিক কনসেপ্ট। আচ্ছা, this is pretty much the end point of discussion for the direct sensing part. Then I'm going to start the remote sensing, so that's why I'm going to stop the lecture, stop the recording, and start a new recording so that we can have remote sensing lecture 1 individually different. This whole chapter of remote sensing is basically what is named as medical physics. remote sensing পুরো চ্যাপ্টারটা মেডিকেল ফিজিক্স। এখানে তোমাদেরকে একটা দুঃসংবাদ বা সুসংবাদ দিয়ে রাখি, সেটা হচ্ছে, let's just